Now, and I'm going to start with those, and then I'll take other questions as well. Hopefully, what I start to cover and answer from those questions are helpful to everyone here as well. Let's take a look at some of the questions that I've been getting and see if we can take a look at some answers here. One of the questions that I have received, which is 16.6b from the suggested homework problems, and asking the question, if we have this conjugated diene system that looks something like this. I feel like that might have gotten a little out of control. Let's try this again. I'm trying to copy it from the textbook here. There we go. So here's the conjugated diene system, and we are going to add HCl to this species, and trying to determine what products would we expect to see as a result. And there seems to be this hint that there will be 4, I'm going to put quotes around that, products. And so what I'm going to do is work through the formation of those 4 different products, and then talk about why we don't see instances of other things. So let's just start out. How would we approach a problem where we're looking at adding hydrochloric acid across a conjugated diene system? And what I'm going to do when I encounter this on an examination is I am arbitrarily going to highlight the key functional group here, or functionality, so that I can start to keep track of where I am going to react things. All right. And so the first choice that I am going to make is saying that once I have identified the carbon atoms about that conjugated diene system, then I need to start reacting one side of this conjugated diene, and then thinking about what is the kinetic product, what is the thermodynamic product, and then reacting perhaps the other diene. So let's take a look at what I mean here. I'm first going to worry about what happens when I react about the carbon 1, carbon 2 double bond first. And so the idea, I'm going to start to take a look at this reaction mechanistically. And I am going to say that if I have HCl present, we know that this double bond will always behave as a nucleophile and react with that hydrogen, and this chlorine will break as a consequence of that interaction. I would then expect to see the addition of hydrogen here, and the carbocation would be placed at carbon number 2. And so this is one of these instances right here where I'm just going to take a brief pause, and I'm going to revisit an idea or a question and say, why didn't, so we'll just say over here, why not this? Addition here follows Markovnikov's rule? Question mark. Interesting. When we add to isolated alkenes, we've always been taught that, well, for like the 4 days that you've been encountering this, you've been taught per se that when we add H and Cl across a double bond, the carbon that has the most hydrogens should be the one that that gets the the proton. And in this case, we have two possible ways that this could add here, and I want to suggest that this is not Markovnikov addition. This is Markovnikov addition hidden, even though you don't see hydrogens at these two positions. And so what do I mean by that, and how we'll see this when we look at carbon 3 and 4 again as a driving force. But what happens? Why not add opposite here? Why not add the proton over here? Well, the reason why is that this carbocation is isolated, while this carbocation is conjugated. This plus charge could exist over here with the double bond existing over here, so we could in instance draw a resonance structure for this molecule that places this carbocation at a more stable allylic carbocation that is stabilized over here. And we'll see that's going to be the driving force for that 1,4 addition. But that aside, right now, we know that this is more stable than this. And well, I've said before, Markovnikov follows the rich get richer, that which has the proton gets the proton. That is not necessarily always true by simply saying there is one more step that is just a little bit richer of a way to say that, which is Markovnikov addition suggests the thing that will lead to the more stable carbocation will get the proton. And so yes, addition, it's not followed here. This isn't Markovnikov addition, but Markovnikov's rule still applies to this type of problem when battling. Should I add the proton to carbon number 1, or should I add the proton to carbon number 2? I think I did that backwards. Carbon number 1 or carbon number 2. And the reason is because it is Markovnikov rule. Even in the absence of protons, the idea of Markovnikov at heart is saying the more stable carbocation is the one that the reaction will proceed by. And that then places this as the more preferential regioisomer to add the proton to, and the light blue is not seen at all. And we'll actually see why that's important on the next one as well. And so at this point in time, then we know that chlorine addition to this plus charge right here will result in the formation of a new chlorine bond right over here. And this double bond will not move at all. And at this point, we have to acknowledge that this carbon right here is chiral, and so we'll actually be getting the actual answer that we would derive from this product right here would be this product and its enantiomer like here. And so here are the first two products that we would expect to see. Both of these products are a result of the 1,2 addition of HCl. Following that, then, we have this beautiful resonance structure of this allylic stabilized carbocation, by which gives us the most stable carbocation. We need a little energy to do that. It is the thermodynamic pathway because it requires a little bit more energy, and we would expect to then generate this as a product as well. But in asking the same question, once we've done that, is this carbon right here chiral? It fails the test for chirality, and therefore this is the third product from the 1,4 addition of HCl to that molecule if we're looking at that from the right hand side going to the left. Okay, C3 double bond C4 next. So now I'm going to try and determine how this alkene will react with HCl. And accepting that this right here, this reactive intermediate, would be the major reactive intermediate that would predominate the reaction. And again, why not come on, train of thought, come back. Why not this? Right there. That follows Markovnikov addition. If I was to add HCl to this alkene, this carbon number 3, has a proton there, and so Markovnikov addition says that this should get the proton. And I'd have 2 protons here. Now I've explicitly drawn both of them, but that which has the proton should get the other proton. And again, that's true for some problems, but it's more of a superficial, topical analysis of what's happening, when the deeper idea that's really there is that the more true way of saying it, the richer understanding, is that the Markovnikov product will be the one by which the most stable carbocation intermediate is formed, and that's still the one in black. Right here, it is allylic stabilized and it is a secondary carbocation, and so it's going to be more stable than just this tertiary isolated carbocation over here. You're not going to see that pathway produce very many products, and if any at all. Adding chlorine then to this right here, yoink, adding chlorine to that will produce the following product. But then again, we have to ask ourselves the question of, is that carbon atom chiral? And the answer is yes, it's chiral. And so at that point in time, we end up forming this and this as the result of 1,2 addition to C3C4 instead of C1C2. I know I'm writing 1,2 addition when I just said we're starting with carbons 3 and 4, but the definition of 1,2 is I'm just going to use that tail end set of carbons first, and we're going to apply the 1,2 addition philosophy to a set of carbon 3, carbon 4 of this molecule. And so here 1, 2, 3, 4, and 5 products. We can draw a resonance structure of this that will then lead us to another possible product. But this carbon is not chiral. This is the 1,4 addition product. And again, 2C3C4 instead. And so now we've got 1, 2, 3, 4, 5, 6 total products that we would expect to see, or 4 unique regioisomeric products, of which 2 of them are chiral and related that way. And so they're enantiomers of one another. A loaded problem. I mean, that just took me conservatively 18 minutes-ish to complete. So ask yourself, is this fodder for an examination to produce these 4 products from a reaction like this? And I'd say, man, that's one hell of a doozy of a question. And if that was on the examination, one thing for those that haven't had me before is sure true. If it's 18 minutes on that 50 minutes exam, it's going to be 18 points, and it's going to require you to take 18 minutes to do it, is kind of the way that I think about it. And so if that's the case, then it's going to predominate the exam, which if I do that on the examination, just know I'm not going to give it 5 points and ask you to do all this. I will find 18 freaking points within this entire question for you to gain in a variety of ways. Now, how would this actually show up on the examination? Let's take a look at isolating some of these ideas here and saying, hey, could you provide a mechanism that leads to the formation of product number 3. Provide a mechanism from scratch. I won't give you anything to help you whatsoever. You provide a mechanism that leads to this question right, or to that product right there, and you would have to draw all of that stuff. Maybe I would say complete the mechanism that leads to the formation of these 2 products. And so maybe I'd give you the skeletal outline, and you would have to provide the arrows, or maybe the CL, or maybe I'd say keep finding things to cover stuff up. There are 2 products that are formed in this reaction. Complete the mechanism and identify the missing parts along the pathway to those 2 products, or something like that. Or maybe I'd say there are 6 products. 2 of them are enantiomeric pairs, and the other 4 or the other 2 are other regional isomers. Here are the partial mechanisms. Not sure how I'm going to do this. Here are the partial mechanisms. Sketch out the products that would be formed. And so you can kind of see there's a few different ways by which I can try and break this sucker up and still get to some of these questions. To ask you to walk your way through the mechanistic study and produce all of these things is just not something that I'm interested in doing to you at all. I don't know what that accomplishes. I don't know quite what that would demonstrate to me that you've been able to do. But filling in portions of some incomplete work, or being able to derive a few of those products, or maybe fill in the others that you don't see, sure, that's certainly fair. Another question that I had is talk about Diels-Alder type reactions where stereochemistry and regiochemistry is involved. And then I had some questions on just kind of online as well, covering the same topic from a previous examination. And let me just bring up an example of what you could anticipate seeing here. Where regiochemistry or stereochemistry perhaps could be involved in some of these questions. And so let's take a look at one. Predict the major product of this reaction, and so this right here would be worth 1.5 points. 1/2 of a point for the correct molecular formula of the product. 1/2 point for the correct regiochemical product, and then 1/2 point for the correct stereochem. And so just know again that there are multiple pathways to get partial credit based on your partial understanding of each of these components of a reaction. For this, let's just take a look. Just really simply, I'm just going to draw the products regardless of the stereochemistry here, and focus more on the regiochemistry, and then we can come back and talk about what is the actual configuration at each of these points. 1, 2, 3, 4. A and B, I have acknowledged what the diene is and the thing that likes the dienophile. And those things reacting with one another, I know that I will form, no matter what, a 6-membered ring that should feature 1, 2, 3, 4, A and B. And there's some parts I'm going to fill in just a second. Or the other way by which this reaction could take place is by forming this 6-membered ring wherein the arrangement of A and B with respect to 1 and 4 is flipped. A and B. That's it. And so if that were the case, then on carbon 1, well, we know for sure these would be the alkene portion, the new portion that's formed. I'm just going to go like this. In red, I'm just going to make a big squiggle line with an OCH3 attached to it. And that's just going to remind us that we've got to come back and figure out what the heck that should be. And then owning the fact that, do not forget this on the examination, that the sigma structure does not change at all. And so if I have a double bonded O attached to carbon A, then I have a double bonded O attached to carbon A as well. And if that then is attached to another carbon that's attached to another carbon that's attached to another carbon that's attached to B, then that framework isn't going to change in the product either. And so I have either this OCH3 configured upwards, and we got to figure out if that's going to be on a wedge or a dash, OCH3. And then the other possibility would be the formation of that regioisomer instead. How do we determine regiochemistry? Well, regiochemistry is determined, if applicable, it's going to be based on electronics. Right here in my diene, I have drawn as one possible resonance structure, by which I could draw another resonance structure that is certainly higher in energy, but features this oxygen attached in a double bond to that carbon and kind of just forces those electrons all around the ring. I've moved some here, I've moved these electrons over here, and moved these electrons over here. I'm not even physically doing that, right? From what we know from MO theory now, these electrons are just zipping across this pi scaffold of the molecule at all times. And so I'm just drawing the more pronounced versions of these. I'm not really even doing too much more than that. Here's an extreme version of this molecule. Here's an extreme representation of the distribution of electrons in this molecule, and here's a much less pronounced one. I'm not sure why I pointed to two things at once here. Here's the more pronounced one, here's the less pronounced one. That's all I'm showing you. And what I'm suggesting here is that's going to be pretty helpful in determining which orientation these two molecules are going to react with. And so the other thing then is taking a look at this dienophile and saying, hey, I can draw this as a resonance structure as well, wherein, wherein I have a single bonded electron now that has pulled the electron density away from that pi bond, which has pulled this portion of the pi bond even closer. And so really, when I'm looking at the more extreme representation of the electronic distribution, then there is the possibility of, and I'm going to make my my hand, the fingers portion of my hand, that's the negative charge on each of these molecules. The way they're oriented right now, both of the negative charges are both pointing downward. They're both pointing like this. And so if these molecules are, and my thumbs are the plus charges on that these two molecules, the alignment that I have shown right here is the one that's going to butt the plus and plus up against one another, and the minus up against one another. And that's just not really that favorable. We want the plus lining with the minus for this nice flow of electrons that we typically get in a Diels-Alder reaction, that nice flow of electrons to occur. And so this configuration, hey, look, that OCH3 up here and this O minus right here, that would lead to this configuration right here. We don't know anything about the stereochemistry yet of this, but certainly this arrangement of the diene and the dienophile approaching one another, that would lead to this product, and this is just not favorable. Okay, it just, again, I can't remember exactly what plus and plus, but you get the idea that this is not favorable when the pluses and the minuses here are on the same sides of the molecule. We want those on opposites. And so, man, it would sure be better if we flip the orientation of the dienophile, and now we have this instance, and that arrangement then is really significantly more favorable, and that's going to lead to actually this one. So you would anticipate seeing that as the major regiochemical product, of which now we have to go back through and talk about the stereochemistry of that OCH3 portion of the molecule. And what I can simply say for that is that if that diene is featuring, so let me just draw a little sidebar over here, and these are the notes that I let's just refer to those. These are the notes that I added at the end of lecture when everybody had left me all by myself from lecture. Hey, notice that if I'm on the inside B right here of this diene, then I appear on the dash over here. And if I'm the outward facing substituent A, then I'm going to appear on the wedge. Almost more importantly than that is acknowledging that, hey, if I'm on the outsides, I'm always going to be on the wedges. And if I'm on the insides, I'm always going to be on the dashes. And that has to do with the way this molecule rotates when it forms these new sigma bonds. When this Diels-Alder portion happens and we get this ring closure happening, it forces these things to close in a certain manner that is always going to force these things in these manners. And so you can always remember that on our diene, these positions are always going to be appear here, And then on our Diena file, the stereochemistry will always appear like that. And so based on what I just told you here, I would expect this substituent to appear on the dash major product for that reaction. Those are two of the... Why is my handwriting so great tonight? Those are just two of the questions. So someone chime in, ask another question that may answer for those that are here. There's terms that are being tossed around about aromatic systems. We did not talk about aromaticity. We did not talk about aromatic systems. That's something that we'll just have to get to as soon as we get back together on Monday. And so all of Chapter 17 is not on this examination at all. And so worrying about that stuff is not something you need to do. Again, the examinations from previous fall, even last semester, do not sync up with the material as we do this in the summer. And so as a result, you wouldn't expect to see that on the exam. So another question that I've seen a little bit is construct an MO diagram for something like a molecule like this. Remembering that really what we're trying to isolate is just the pi portion of the molecule, the p orbitals. And for us, we're just going to be looking at the contributions from all of those carbon atoms. So we'll be looking at the p orbitals, 4, 5, and 6. So how can we combine these 6 p orbitals, each which has one electron, one pi electron in the system? So coming from carbon 1, 2, 3, 4, 5, and 6. Well, if we want to construct an MO diagram here for this system, and again, we're just looking at the pi portion. You don't have to worry about the sigma portion. These 2 carbons right here, those, we don't have to worry about those. They're not part of this pi system at all, so we don't have to worry about that. We know that there will be a total of 1, 2, 3, 4, 5, 6, total molecular orbitals that are part of this system, of which all of these are bonding orbitals, all of these are anti-bonding orbitals. This would be the highest occupied molecular orbital, the lowest unoccupied molecular orbital. I'm just going to fly through this really quick, but you can, before I even start drawing any of the pictures, not even knowing if I would ask for that on an examination this weekend, but just, you know, look at how much we can already deduce about the molecular orbitals of this molecule, at least the pi portion of the molecular orbitals of this molecule. We have so much that's rich here that we can pull from, that we don't even need to know the pictures. We know which is the highest occupied. We know which one's the lowest occupied. We know how many there are. We can already tell which are anti-bonding, which are bonding. And so there's a lot there that you can know without really having to know everything about the actual shape of the molecular orbitals. But I'll do the hard work. The lowest energy molecular orbital is this one, and the highest energy molecular orbital would feature nodes in between each and every single one of those atoms. And so you're likely to see the handwriting deteriorate here, but here's how the shading would occur here. And so one big node here, increasing the number of nodes in the molecule increases the energy, because there's now a section of the molecule that that is there's no bonding allowed, and look at how many there are here. 3, 4, 5, 6. It looks like I went way overboard here, so let's just pretend these don't exist over here. But certainly you get the idea that there's a large number of nodes present over here that increase that energy. We now are responsible for putting 2 nodes into the next molecular orbital, the next highest energy one. So there's a good way to add 2 nodes. We now need 3 nodes in this molecule, and remember I told you that we want to try and do the absolute best that we can to preserve the bonding in certain portions of the molecule if possible, and so we want to keep it symmetrical, and then we want to keep as much of the bonding in the middle as possible, not at the tail ends. And so we would have an MO that would look something like this. And then we have to do 4. Whoops. We'll preserve the bonds in the very middle of the molecule, but now you can see these tail ends are starting to just fall apart. And that ends up being a well-constructed MO diagram for the pi portion of that molecule. Other questions that people have? Well, if there aren't other questions, good luck with your preparations. Consider yourselves lucky you were here because I'm not sure all of that was recorded. We'll post whatever we get. Good luck with your preparations for the examinations. There'll be some instructions for you online on Sunday. Have a fantastic Friday evening.
I have a quick question. Sorry.
Yeah.
I sent you an email with a couple of questions with. Time is a little short, so I'll just go with the more important one I have. It was a question 8 on. It's on an email I sent you. It's called review questions. Would like synthesis and like that big chart be like something we could see on the exams?
Yeah, absolutely.
Okay. Do you have time to work out the synthesis of the starting with the benzene? Propose an efficient synthesis for each of the following product.
Yeah, have we dealt with benzene yet?
No, we haven't. No, so okay. Okay, cool. Never mind then. No, that's fine then. Yeah. Okay, I'll try to find one in the books to look over. All right. Thank you.
Yeah, good luck.